I'll start with just because this is an unusual week because of the wellness days, I want to go over a few logistics because I screwed up and forgot to remember the wellness days. So there's going to be a little bit of schedule reorganization this week. The first, with regard to labs this week, we're not going to host lab sections on your wellness days. We're not allowed to host sections on your lab sections on your wellness days. So what we'll do instead is we're going to call today's lab section office hours. So anyone can come to today's section if they want to work. And then I'm also going to host office hours as usual on Friday afternoon. So if people want to come and talk through any Boyd's bugs this week before your checkouts next week, you'll have the opportunity to do that this afternoon or Friday afternoon. And if neither of those times work for you, reach out to me. But please try to, if you want to come work, please try to make one of those two sections. The other schedule modification associated with wellness days is we are not allowed to have, and it's a good rule, we're not allowed to have anything due on wellness days. And we're also not allowed to have anything due on the day that you return from wellness days, which would be this Thursday, the 11th. So what that means is groups that have lab reports due. So what that means is I am going to push the due date for everyone's Lab 1 report, including the Monday people who probably already turned things in. So I'm sorry about this. This is just an oversight on my part. But I'm going to push everyone's Lab 1 report due date to Friday. So I'll update that on the Canvas site this afternoon. I'll also put an announcement on Canvas this afternoon just to remind everyone of that. But that's so you don't have to turn in any assignments over your days off. Any questions about that? And you should take some time off on your days off. Go for a walk or something. It's supposed to be really nice this week. Before I get into content, there's one thing I wanted to share with people because I think you'll find this useful for trying to get the most Boyds that you can. In your, I share screen and like everything gets rearranged. Okay, so in the MPLabX environment, you can change the amount of you can change your compiler optimization level. So GCC, the compiler that we're using, has various optimization levels. By default, it's set to 0, which is the least amount of optimization. With the free version of MPLabX that we're using, you can turn that up to definitely to optimization level 1 and maybe 2. I'm not sure. People can try this. But if you want to do this, and you should, the way to affect your optimization level is to go to the Run menu, Set Project Configuration, Customize, select the GCC option here. In option category, select Optimization. And then from this drop-down menu, you can select a higher optimization level. This will get you for free, maybe like 10% more Boyds, maybe even more than that. So it's a good thing to be aware of. So once you've got everything working and you're satisfied with your flock and how it's behaving, go in and turn up the optimization and see how many more you can add. You will get a lot for free, which is nice. Okay. Any questions about any of that stuff? Okay, so my plan for today is to go over direct memory access, which, like I mentioned in a previous lecture, is something that is not directly relevant to any lab that we're doing, but it's a powerful hardware peripheral that's on the PIC32 that many of you might find useful for your final projects. So I feel like it's a good thing to cover. It's also just in a microcontrollers course. We should cover direct memory access. This is a hardware peripheral that's on a lot of microcontrollers, and it's a powerful one. No lecture on Wednesday because of your day off. And then on Friday, my plan is to introduce Lab 3 because our Lab 2 checkouts are going to be Monday, Tuesday, and Wednesday of, well, they're going to start a week from now. So Monday and Tuesday, Wednesday, a week from now, which means Friday is a good day to introduce Lab 3. I'll remind you that your final project proposals are something like 3 weeks off. So really start thinking about this. And I think next week, probably, if people would find this helpful, we can dedicate all or most of a lecture to just brainstorming final project ideas. I know I've talked to a number of people that are still kind of not really sure at all what they like to do, and that's fine. So maybe folks would benefit from just kicking around ideas as a group, and we can schedule that in if that would be helpful. Any questions before I get into content? Okay, let me just check okay. So yeah, I see in the chat that Parth was able to get 2, so that's good. Okay, so I want to cover direct memory access today. The way that I want to talk about this is I want to talk for a few minutes at a high level just about what this peripheral is and what it's generally good for. And then there's some vocabulary associated with the direct memory access peripheral in particular. So I just want to go over some terms that you'll see in the documentation associated with DMA. So we'll talk at a high level about it, go over some terms, and then as usual, we'll look at some example code to see how this is actually implemented in your software. So what is DMA? DMA is it's a hardware peripheral that you can think of as a very simple coprocessor that can only do a very limited amount of things. And what the DMA coprocessor can do is move information, move data from one place in memory to another place in memory, completely separately from the CPU. So why is that useful? Well, that's useful on a chip like the PIC32 because all of the hardware peripherals that we've been discussing in this class, discuss the SPI hardware peripheral, the UART hardware peripheral, all the other ones, these are memory mapped. So what that means is there's particular addresses in memory on the PIC32 where that particular peripheral will go to look to take some action. So to take the example of the SPI channel, there's a particular place in memory where the SPI hardware peripheral goes to get information to send through the SPI channel. So if you aim a DMA channel from one place in memory to, for example, that SPI transmit buffer, and you shuffle data into that transmit buffer, if you have everything configured properly, then you can have the SPI channel automatically transmit some array of information without any interaction with the CPU. Being a little sloppy with language, but by no interaction with the CPU, what I actually mean is no software cycles of the CPU are being executed. All of this is happening separately and in parallel. It's hardware parallelism. It's a separate parallel peripheral device, a simple CPU that is running in parallel to the main CPU. So the challenge with this device, it's one of these interesting things because it's highly constrained in that it's not as flexible as the main CPU, but if you can aim this thing properly and turn it on, it will just run and you can stand back and watch information flow around with no interaction with your main CPU and without sacrificing any cycles, which you're using for whatever application that is actually important to you. And you can do other interesting things with this. So if we're going to talk through a lot of, these channels take a lot of configuration. This is where a lot of the vocabulary for these channels comes from. But all of the configuration comes from, if you think about, if you were to ask a CPU to move data from one place to another place, and you want that to be done properly, there are certain degrees of freedom that you have to specify. And essentially all the vocabulary that we go through is just basically naming these various degrees of freedom. So for example, you will obviously need to point this hardware peripheral to the source address, the address from which you would like for it to start reading memory. And you're going to need to specify a destination address. Where do you want for it to put the information that it's getting from one place? You're going to need to specify, you need to tell it, how does it know when to start this transfer? That's a configuration that you have to set up. Is it going to start based on, generally speaking, it will start when it sees some sort of an interrupt flag, and you can configure that. Is it going to start a transmission when a particular timer overflows? Or maybe it'll start a transmission when it sees an interrupt flag thrown by an SPI channel or by a UART channel. All of that is up to you to configure. When is it going to stop transmitting? That's another configuration that you have to set up. You might configure it so that it never stops unless you go in and software and abort it. And it can just continue to transmit some array over and over again to some destination address. Or maybe you have it stop when it sees a particular sequence of bits in the memory that it's transmitting, so-called matched mode. So you can have it transmit through an array, and when it sees a particular a particular bit sequence in one of the bytes or one of the pieces of information that it's transmitting, it can be configured to stop. You can have it configured to stop on an exception, a divide by zero error. You can have it stop on that. So there's lots of configurations, but if you put in the time up front to get all of these configurations correctly, then you can just stand back and watch all the information flow past, and it can offload a lot of work from the main CPU into this peripheral channel. Okay. Questions about this? So that's just a lot of words. We're going to actually look at some examples here in a moment, but I want to just talk generally about what this thing is good for. It's a simple coprocessor for moving data from one place in memory to another place in memory. And the reason that that's particularly useful on this particular system and a lot of other systems is the hardware peripherals are memory mapped. So if you move data from one place in memory to a specific place in memory associated with a peripheral, you can interact with that peripheral without sacrificing cycles of your main CPU, software cycles of your main CPU. Okay, so let's look at just some vocabulary here. I'm on, incidentally, the DMA page for the course website, so the DMA webpage. So just a few pieces of terminology. The first piece of terminology is you'll see in the documentation this word event. An event is any system that can initiate or abort a DMA transfer. Generally speaking, for us, these are interrupt flags. So an interrupt flag is an event which can initiate or abort a DMA transfer. And it's just the flag, incidentally, that initiates or aborts the DMA transfer. You do not need any interrupt service routine. This coprocessor is just keeping an eye on flags, and when it sees a particular flag for a particular interrupt, it knows to go, or it knows to stop, however you've configured it. So for example, you might set up a particular timer, say timer 2, to overflow and throw its interrupt every time it overflows. You don't need to write an interrupt service routine associated with timer 2 in order to have timer 2 throttle your DMA channel. You can configure a DMA channel to just keep an eye on the timer 2 interrupt flag, and every time that timer overflows, a DMA transfer will be initiated. We'll see an example of that. Any interrupt flag, though, doesn't have to be a timer. Could be an interrupt flag associated with some other hardware peripheral. So you can chain these things. It could even, incidentally, you can configure a DMA channel to throw an interrupt when it completes a transfer. We have on this chip, is it 4 or is it 5 DMA channels? I think it's 4. We have 4 DMA channels on this chip. So you could configure them, if you want to get a little twisted, you could configure them so that a particular DMA channel does a transfer, throws a flag when it completes that transfer, which causes a separate DMA channel to do a transfer, throw a flag when it's done, and you can daisy chain these things so that you have DMA channels triggering DMA channels, moving data all around the CPU without any, or all around the device without any interaction with your main CPU. What makes this, if you really want to get complicated, you can have the DMA channels write to the control registers of other DMA channels. So I mean, you've got to stare at the ceiling and squint for a while to think about how this might be useful, but if you do it for a while, you could start to come out with some pretty weird things that you might be able to do just by having DMA channels interact with other DMA channels. Especially because they can make decisions based on the information that they see. They can stop on a match, right? So it starts to almost, you could almost twist your mind in such a way that You think, could I make a really simple CPU out of just having DMA channels interact in complicated ways? Maybe, I don't know. I haven't tried that.
You can. It is Turing complete. Move command is Turing complete.
Okay. So in any case, that is what an event is. An event is just something which initiates or starts a DMA transfer. For us, those things, generally speaking, are interrupt flags. A transaction is a single word transfer, which is up to 4 bytes long. So it is you could think of this as the smallest quantification of a transfer amount. A transaction is a single unit of data moving, and that unit is going to be up to 4 bytes. A cell transfer is the data transferred when a DMA channel has a transfer initiated by a single event. The channel then waits for another event. So it sees the event, and what is the action that is caused by seeing that event is a cell transfer, which is a transfer of some amount of bytes. And this can be a lot of information, incidentally. You can configure a cell transfer to be up to 65,535 bytes transferred on a single event. A block transfer is comprised of one or more cell transfers. So you can have a single event cause multiple cell transfers. So if you have some very large piece of information stored in memory, maybe it's some array of 32-bit ints, you can have a block transfer, which is the transfer of that entire array started by a single event, but it can be composed of a bunch of separate cell transfers. So the DMA channel will send this 32 bits, and then this 32 bits, and then this 32 bits, each in a separate cell transfer, but it can transmit that whole block in response to a single event that it sees. So for example, maybe you have a very large array of data that you want to send to the DAC to produce a sound, and you want to send the data to the DAC in response to a single interrupt flag. But you want to break that transfer up into a bunch of different chunks so that the DAC can receive 16 bits at a time as the data sheet specifies it must, right? You can do that. So you can have the DMA channel send some very large piece of information, but do it in a controllable size, a certain number of chunks of configurable size. Does this make sense? Okay. And then, like I suggested, these DMA channels have a bunch of different modes, and we'll see some examples of this in code in just a little minute, or in just a minute rather. But I want to talk through just a few of these in words first. So basic transfer mode. Basic transfer mode, if you configure a DMA channel to basic transfer mode, what that means is in response to a single event, it does a single transfer. Could be a block transfer, right? But it does one transfer per event. This is in contrast to something like auto mode, where you can configure a DMA channel in response to an event, it will look through some section of memory and transmit what it sees in that section of memory to another section of memory. And when it completes, it can go back to the beginning and do it again indefinitely, over and over and over and over again. Until you abort it, it will just continue to transfer a particular section of memory that you've configured it to transfer. As I suggested, you can set these up in chaining mode so that one DMA channel terminating triggers a second one to start, and you can configure them to ping pong off one another if you want to. And you can set them up in pattern match mode, where you can have a DMA channel continue to look through memory from some starting position. It will look through memory and continue to move that memory until it sees a particular pattern, which it uses as the signal to stop the transfer. So why is something like this useful? We'll say suppose that you are sending strings received over a UART channel. In C, we know that strings are always null terminated, right? So the end of a character string is always indicated by the character of all zeros. So you could set up a DMA channel to transmit from the start of some buffer that will contain that string until it sees the null terminating character. And then as regardless of how long that string is, it will transmit the whole thing until it sees the end of it. And then it'll stop transmitting. We see this too in our Python code that we spent some time looking at. You'll recall that every one of the serial transmissions that we send to the PIC32 is terminated by a carriage return character, \r. If we have time today, we'll look into the proto-threads header file and we'll see that there's a DMA channel configured to match mode. And that DMA channel stops moving information from the UART receive buffer to that PT term buffer when it sees the carriage return character. So this means we can send some arbitrary, essentially an arbitrary length string in, and the DMA channel will keep on grabbing more information from that string until it sees the carriage return character, and then it will stop. So there's a lot of, there's a bit of vocabulary here, but like I said, a lot of this vocabulary is just basically relating to, it's giving names to a few of the degrees of freedom associated with a peripheral like this, right? How does it know when to start? How does it know when to stop? How big are the chunks of data that it sends? How big is the total amount of data that it sends? These are all configurations that you have to set up. So we can look at this in code, which will hopefully help solidify some things. So I put together, I tried to think of what's to strip out. I've tried to put together a demonstration that showed DMA and DMA only. So strip out everything not related to this demo and just show a DMA channel. So the demo that I put together here doesn't even include proto-threads. It is just a simple file that includes a single main function in which we configure a DMA channel and enable it and then watch what happens. So what is this? I'm going to run this in a moment, but what is this demo doing? So what we're doing here is we are importing this file hellosound.h, which if we look at hellosound.h, all that this header file contains is a very large array called DAC data. It's an array that is basically 10.5 thousand elements long. Each of these elements is 16 bits. So that's 2 bytes. So this is about a 21 kilobyte array, where each element of this array is 16 bits. The information in this array is, I recorded myself saying hello, and then I imported that sound file into a Python script and truncated each of the samples down to 12 bits. We have a 12-bit DAC. And then I appended to the top of those 12 bits the control bits associated with the DAC. So you'll remember from the demo code that we started this class with, these configuration, DAC config channel A, DAC config channel B, you'll remember from this file and you'll remember from the data sheet that we went through that the top 4 bits of the 16-bit word that you send to the DAC are configuration bits. You'll recall that the top bit tells the DAC, are we sending this to channel A or channel B? One of these is a reset bit. There's configurations, right? And then the bottom 12 bits is the actual data that you want the DAC to convert to a voltage and output. In lab 1, we computed the 12-bit data, and then before each SPI transfer, we appended the 4 configuration bits to the top of those 12 bits to form a 16-bit word, and we sent that. When we're using DMA, the DMA channel is just going to scan through this array, grab an element out and send it to the DAC. So we need for the configuration bits associated with the DAC to be already built into each element contained in this array. So each of these elements is 16 bits long. The top 4 bits are those configuration bits, and the bottom 12 bits is the actual data that we want for the DAC to output. So this is just a huge array. You can see I've labeled this const, so this is getting stored in Flash. Huge array. And what we now want to do is configure a DMA channel to go to the start of this array, and at a very precise rate, at audio rate, we want for it to move information from this array to the SPI transmit buffer. And then we've configured the SPI channel into framed mode. We talked about this a few lectures ago, but you'll recall that in framed mode, when you put a piece of information into the transmit buffer, it just transmits, right? So we want for the DMA channel to, at audio rate, step through this array, move each element of the array from its present place in memory to the SPI transmit buffer. When it lands in that transmit buffer, it will just get transmitted to the DAC. And then at one audio sample later, it will move to the next element of the array, transmit that, and it'll also go to the DAC. And when we do that, we will hear coming out of the DAC me saying hello, with no interaction from the no interrupt service routine, no audio interrupt service routine, nothing. It's all just happening behind the scenes. So how do you actually do this? So we import that file, which, like I said, just contains a huge array. Pound define a variable here that is just the length of the array. And then we drop into main. The first thing that we do here is open timer2. You've seen these sorts of plib function calls before, but we open timer2. We turn it on, internal source, prescaler to 1, and we have this configured to overflow every 907 CPU cycles. Why 907 CPU cycles? Because when I recorded my voice, I looked up the sample rate that the recorder used to record my voice, and it turns out it was 44.1 kilohertz, I think. So in order to send that data back out at exactly 44.1 kilohertz, we need for this to overflow every 907 CPU cycles, where the CPU is running at 40 megahertz. 40 megahertz divided by 44.1 kilohertz gives you about 907 cycles. Okay. So we open up this timer. Notice we did not turn on any interrupt service routine. It's no interrupt service routine. It's just a timer that's overflowing every 907 cycles. We then open up our SPI channel, SPI channel 2, turn it on, 16-bit transfer mode, master mode. We set the clock polarity to what we need for it to be. We enable framed SPI mode, and then we set the SPI clock divider to 2, because you'll remember that the DAC's maximum baud rate is 20 megahertz. If we're running the CPU at 40 megahertz, we want to divide that down to 20 megahertz. Okay, so we open an SPI channel. This is exactly like you've seen before, with the only difference being we're opening it in framed SPI mode. And this is so that we don't have to, in software, toggle a chip select line. Instead, we have an additional peripheral pin select mapping here. You've seen this one before, right? In this line, what we're doing is we're doing a peripheral pin select mapping of the SDO2 signal to GPIO port RPB5, which happens to be in group 2. Okay, so you've seen this before. We now have another one where we're saying the internal signal SS2, this is the chip select signal for SPI channel 2, we're mapping to RPB10, which happens to be in group 4. So in addition to mapping the MOSI line, we are now also mapping the chip select line because we're opening this SPI channel in framed mode. So it will automatically toggle that chip select line. In order to do that, it needs to know which IO port the chip select line is actually mapped to. But okay. Then we get into the actual DMA configuration. So we open a DMA channel by calling DMA channel open. We specify which DMA channel we want to open. This could be 0, 1, 2, or 3. because there are 4 DMA channels. We specify the priority level of this DMA channel. This is relative to other DMA channels. So this could be a value up to 4, I think, but I'd have to check the documentation. In any case, you can give some DMA channels higher priority than other ones if you want to. In our case, we only have 1, so it doesn't super matter. So we give it a priority level 0. And then we open it in auto mode. And you'll recall that opening a DMA channel in auto mode, what that means is we'll point it to the beginning of the array that we want for it to start transmitting from, reading from to transmit to somewhere else. It will move through the amount of memory that we specify, and then go back to the beginning and do it again over and over and over and over and over again. So we open the channel, and then we configure the transmit, or the transfer rather. So we can look at it. I might have to pull up the documentation to remind me of each of these fields, but we point it to this is the place in memory where we want for it to start reading from. Remember that an array in C, the name of that array is a pointer to the beginning of the array. So what we're passing here is a pointer to the beginning of an array called DAC data, which is this here. So we're pointing it to the beginning of this array. This is the memory address that we're pointing it to. We're specifying the place in memory that we would like for it to move data to. In this case, we're moving it to the address of the register named SPI2buff. And you'll recall from our SPI discussion last week, I think, maybe 2 weeks ago, when we opened up the hardware reference manual, it told us all these register names. So we could go to that hardware reference manual, or you could go to the data sheet for this device and figure out what's the name of the register associated with the SPI channel 2 transmit buffer. Turns out in this case, it's SPI2buff. Okay, so we're transmitting data from this DAC data array to the address of this SPI2 transmit buffer. We're specifying how much data we want to transmit, how many transactions do we want to occur. We want for it to do a number of transactions that is equal to the length of that array, which is large table size. We specify the size of the, so in other words, this is the size of the information source. We specify the size of the information destination. In this case, SPI2buff is 2 bytes wide, 16 bits. So we specify that here. And then this last field, we specify the size of the chunks that we want to transmit this data. So we want to transmit this whole array in 2-byte chunks, 16-bit chunks. So we configure that here. So what this DMA channel will do is it will start at the beginning of this DAC data array, and 2 bytes at a time, it will increment through this array and move what it finds at each address from this array to the SPI transmit buffer. And it will keep doing that until it has executed a number of transfers that is equal to the size of this array. And then because we've configured this in auto mode, when it completes, it'll go back to the beginning of that array and do it again, over and over and over again. If we had opened this in default mode, then it would do it once and stop, and it would wait for a signal to start again. And we would have to configure what that signal is. Maybe it's a signal from software, maybe it's some sort of an interrupt flag, but we would configure it. In our case, we've configured it so that it just does this over and over again. We set the event control. So the 1 here is, the first element of both of these, the first argument of both of these function calls is the DMA channel. So we're configuring DMA channel 1. So we're setting the event control for DMA channel 1, and we're saying the DMA start interrupt, the signal to you DMA channel to start your transfer, a particular transfer, is going to be the timer 2 interrupt flag. And remember, we've configured timer 2 so that it throws its interrupt flag at precisely the audio rate that we want. So what that means is this DMA channel, every time it sees that interrupt flag, it will send a new 2-byte transfer from that very large array to the SPI transmit buffer. So that means we're moving information from that array to the SPI transmit buffer at precisely audio rate, and we're moving them in 16-bit chunks. We then enable the channel, and then, this is what's interesting. This is main. In this example, I don't have a while one loop. So when we reset this CPU, it's going to start at the top of main, execute this line of code, et cetera, et cetera. It gets down, it executes this final line of code, and then it exits main. What usually happens when you exit main? Your code hangs. Nothing happens, right? The CPU is going to looking for at particular places in memory for instructions. Once you leave main, there's no operating system on these devices, right? So once you exit your code, there is no, you're in oblivion, right? I don't know, it might be trying to execute something, but the symptom that you'll see is everything stops, right? Everything stops executing. So in a normal, well, not normal, in an application that doesn't use the DMA channels, once we exit main, that's it, we're done. Until we reset the CPU, it will execute everything in main again. And then once it exits, all execution stops. This is why, generally speaking, we have infinite loops in things like our threads, and in a program that doesn't include proto-threads, your main function would include a while one loop that you never exit. You see this in things like Arduino, right? Arduino has that loop function from which you never exit, because if you exit, you're done. But this is different because we've configured this DMA channel, which, like I said, it is a co-processor. And we have programmed this co-processor by writing to registers. So we've configured the registers associated with this DMA channel in main. So now that DMA channel co-processor is programmed. And even though we exit main here, it's going to continue to run. So let me show you what this looks like. This is exactly the same code that we've just been looking at. I've programmed this onto a PIC that's on the desk next to me. When I unmute this, what you will hear is, despite the fact that we've exited main, despite the fact that the main CPU is doing nothing, the DMA channels are continuing to move data from that DAC data array to the SPI transmit buffer. The SPI channel is configured to framed mode. So as soon as it sees data in that buffer, it sends it. So we continue to see things happen because we've chained together a bunch of hardware peripherals, and all of those hardware peripherals are now self-sustaining. The DMA channel is triggering the SPI peripheral. The SPI peripheral is configured to automatically transmit when it sees new data. And we've configured the DMA channel to auto mode. So when it finishes, it just goes back to the beginning and does it again. So here's what this sounds like. It's really annoying. That's me saying hello really quickly over and over and over and over and over again. And if we pull up I have the oscilloscope hooked up to the DAC output. And what you can see is this is the waveform for my voice saying hello. And it's repeating over and over and over and over again. With definitely no CPU cycles software cycles being executed, right? Because we've exited main. The CPU is not doing anything. All of this is happening on the DMA channel coprocessor on separate dedicated hardware peripheral devices. So what this implies is, suppose you set all this up. Let me pull this code up again. Okay, suppose you added code like this to your main function in your Boyd's lab. Suppose you put some array in Flash that you wanted to transmit to the DAC, okay? And suppose you configured a DMA channel like this. You could have your PIC32 it could be producing sounds constantly, and it would not affect the number of Boyds that you could simulate. It would have no effect on that. Because this isn't spending any CPU software cycles. So you could continue to spend exactly the same amount of cycles that you're presently spending on doing Boyd's animation. You could do all of that, and in addition to that, have the PIC32 be producing sound. So it's interesting in this way. It allows for you to do stuff with this device without sacrificing any software cycles. And by the way, I'm using the DAC here in the SPI channel just as an example of interacting with a hardware peripheral. But generally speaking, like I said, all these hardware peripherals are memory mapped, including, for example, the analog to digital converter. So maybe instead of having a DMA channel move data from an array to the SPI transmit buffer, the SPI peripheral device behind the scenes, maybe instead you configure it to go move data from an analog to digital converter buffer to memory, also behind the scenes, so that you can sample from an analog to digital converter at a configurable rate. You can configure that DMA channel like we did here to go get a new source throttled by some timer, right? Based on some timer overflowing, moving those analog to digital converter samples to some array in memory that your software can access, but you would have no interrupt service routine. All of this would just be happening in parallel, behind the scenes. Behind the scenes, maybe that's not the right way to put it. In parallel, using this separate parallel hardware. And by the way, in this example, we have throttled these DMA, the speed of these DMA transfers to audio rate. You can move data fast with these channels, up to, what's the fastest you can move? I think like 3.2 megabytes a second. So if all you wanted to do was move data from some place in memory to another place in memory as fast as you could, you can do it fast with a DMA channel. This would essentially replace something like a mem copy. Instead of calling memcopy to move information from one array to another array, one place in memory to another place in memory, you could configure a DMA channel to do that. And all of that would occur faster and in parallel. What do people think about this? It's a lot of configuration. It's an example of something that requires, you need to do a lot of thinking and planning for setting all of this up. But then once it's set up, it just runs and you don't interact with it really anymore. I don't know if any of you play like Factorio, right? But the idea is you get everything set up. It's a video game. Get everything set up and then you click run and everything just goes. So it's all, DMA channel is all about configuration.
I have a question.
Got a question. Does the DMA stop get to the end of the array in the hello.h file then? Is the person is this question actually about truncating the sequence or what?
Yeah, I'm a bit confused about, like, we said it doesn't stop even though the main has stopped. Like, so when, like, I'm not sure, like, what happens when it gets to the end of the array in the hello.h file.
So as we've configured it, we've configured this channel to auto mode. If we go incidentally to, I want to show you in plib. We can see all the modes that we can open this in. So we've opened this in auto mode. What that means is that when so we've told the SPI channel how many transfers to do, and we've told it where to start those transfers. In auto mode, what that means is when it completes this amount of transfers, it goes back to the start address and does it again. Over and over.
And just to be clear, does the array that you showed in the hello.h file contain the address or the actual data?
The data.
Okay.
The data. So all that this contains is, each of these is 16 bits long. This is in decimal format, but these numbers are 16 bits long. The lower 12 bits of those 16 bits contain the data that we want for the DAC to convert to a voltage. And then the upper 4 bits are the DAC configuration bits. And in previous labs, we sort of appended these things right before we sent it to the SPI channel. Because the DMA channel is just grabbing data and throwing it into the transmit buffer, we need for these configuration bits to be appended to every 12 data bits beforehand. So we do that work up front, and then the DMA channel just screams through here and writes stuff to the DMA, or to the SPI channel rather.
I see. Thank you.
I have a question, Hunter.
Mm-hmm.
In your code, what's happening is that as soon as the timer hits, let's say 907 cycles have passed, then the indexing of the array shifts by 1. Then it again goes and goes again and again and again, and the data is sent to the SPI, right?
Yes.
And there is no event that's, let's say, I mean, this is in auto mode. Let's say I want an event to occur when I'm pressing a button, and as soon as I hit the button, the audio transmission occurs, but only once. So first of all, I'll have to configure it in default mode instead of auto mode, right?
Yes.
And what function will be used to start the transfer?
So in that case, you could instantiate the transfers from software. Why in default mode, every time you would call this DMA channel enable, you could start a block transfer. Now, what you don't want to do in software is you don't want to use software to instantiate cell transfers, the small unit of transfer. But it does make sense to use software to instantiate a block transfer of lots of data. So in response to a button push, you could call DMA channel enable. That would send the whole array out to the DAC and produce sound. But you would have only had to spend basically, I don't know, probably 1 or 2 cycles just calling DMA channel enable to cause that whole block transfer to occur.
And it will disable the DMA channel after it's done. It will automatically disable it.
Yes, it will stop moving data. It will stop moving data.
If it's in default mode.
If it's in default mode. I screwed this up this weekend, by the way. I've been working on DMA on a different device, the new Raspberry Pi microcontroller. And I was sending information from a particular place in memory out to the DAC and configured it incorrectly. And ended up, it kept happily traversing beyond the end of that array into other parts of memory and sending it out to the DAC. So it's kind of interesting because you end up with what looks like a mess on the oscilloscope screen because you're just outputting whatever's in memory to the DAC. But it'll happily do that kind of stuff for you.
I had another question. For instance, the array you have initialized is a one-dimensional array with lots of data at every element, right? Let's say that I have an audio where a lot of it is just dead silence. So how do I configure it to send sparse matrices?
Can't.
Yeah.
Okay.
There's no gather scatter. There's no stride. It has to be densely packed data.
Okay.
Other questions? So why might you find this useful in final projects? Maybe if you're building a video game and you want sound effects, right? Maybe it makes sense to produce sound effects using a DMA channel so that you don't have to spend software cycles that you might otherwise spend on game animation on audio synthesis. Requires a slight rewiring because we have to map that chip select line if you want to do this to set up the SPI channel in framed mode. But I could make that remapping for you. I could do that jumper for you.
For amusement's sake, last year, an undergraduate and I did convert DMA channels into a general purpose CPU. It's you talk about head scratching, as Hunter said, you gotta squint at the ceiling a lot because this intensively used DMA channels to write DMA control blocks. Also, the only way to read the A to D converter at full speed, which is 1 megasample a second, is to use direct memory access. You cannot interrupt the CPU fast enough to do that.